Okay, so how can I check that the matrix that I calculated is actually the matrix representation for t with respect to those bases? Well, if t of v should be that matrix times v when I express v in x coordinates. This should pop out t of v in x coordinates. So if I take a generic vector v in here, once again, it's a generic 2 by 2 matrix. So let's consider a generic 2 by 2 matrix. Then if I write that as a linear combination of these basis vectors, I have a times the first one plus b times the second one plus c times the third one plus d times the fourth one. And so if I write this in x coordinates, I get that. So what I'm going to do now is take my matrix M times that column vector. Alright, so here's the matrix M from before, and here's the column vector representation for a generic 2 by 2 matrix. And I go through the usual row column. So I take row times column, I get a 0. Row times column, I get b minus c. Row times column, I get negative b plus c. Row times column, I get 0. Remember, this is the x-coordinate representation of a matrix, so what's this correspond to? It's 0 times the first basis vector plus b minus c times the second basis vector plus negative b plus c times the third one plus 0 times the fourth one. And so when I work this out, I get 0 b minus c, negative b plus c, 0. The question is, how does that matrix compare to the image of any generic matrix? So let's take T of A, B, C, D. By definition, it's the matrix minus its transpose. A minus A is 0, B minus C, C minus B, D minus D. And if I just rewrite things just a little bit, you'll see that's exactly what I got before. All right, so that's how we can check that our matrix representation is doing its job. That'll do it for Take Home 5.